Hi everyone. It's been more than 2 months since my last video. And the reason it took so long is because, well, a lot of distractions basically. Like for example work. I had to design and build several industrial inspection systems. And just when I got to finishing up this video, the aftermath of a huge fire right next to my workshop distracted me again. Now I consider myself very lucky that only the facade of the building got damaged and none of my machines or projects. But there were also very nice distractions, like this sweet little magpie that got dumped by his parents. It needed a little love, guidance and, well, food basically. By the way, did you know that magpies are among only very few animal species that actually pass the mirror test? They're very smart. Anyway, I'm getting distracted again. So this video will be on optical mirror surfaces that have a variable shape. And with this kind of mirror, it's possible not only to change the radius of curvature, but also the conic constant. And because you might very well be a bit rusty on the term conic constant, next up is some theory on this subject. Later in this video, I will show you how I actually made the variable mirror and how I measured its properties. So if you're just interested in that part, it's best to skip ahead about 10 minutes into this video. If by chance you are an amateur telescope maker and you've made your own Newtonian telescope, you will probably know that in order to create a sharp image of the sky, it's best to make a parabolic mirror and not, for example, a spherical one. And the reason for this is pretty straightforward. So let's assume that we would use a spherical mirror to look at the stars. Now, as you can see in this schematic, a purely spherical mirror would not give you a well-defined focal point. So rays reflected in the very center of the sphere will reach the focal point quite well, but as we move from the center to the outside of the mirror, the rays are reflected to points further and further behind the focal point. And this effect is known as spherical aberration, and it causes unsharpness and loss of contrast in the projected image. So here the effect is strongly exaggerated, but normally we would use a mirror that contains only a small fraction of the total surface of the sphere. But even then, if you zoom in on the focal point of a spherical mirror, the aberration is always there. Now, if you would use a parabolic surface in this situation, you don't have this spherical aberration. So in a parabola, the curvature is such that each ray parallel to the optical axis is reflected exactly towards the same point. And in addition, the distance traveled by each ray is identical. And that's also important if you want to keep the wavefront in phase for all rays. But let's take a step back. So what if you're not looking at an object very, very far away, but instead at an object at a smaller distance? What's the ideal mirror shape then? So let's assume we have 2 points and we want to collect the light coming from point 1 into point 2. So if we reconstruct the total reflective surface required for this, the basic mirror shape is in fact an ellipse. And in this case, the total distance traveled for each ray is also identical. But making a mirror that contains a large portion of this reflective surface would not be feasible for a telescopic device. So instead, we just use a tiny section of the total surface and we are satisfied with the limited amount of light that is collected by this small part of the total surface. By the way, there are applications where a full elliptical shape is used to transfer light from one point to the other, and that's for example in the construction of certain laser cavities. Here we have a linear flash lamp located in one of the focal points and a laser rod in the other one. And this allows you to get all the light from the flash lamp efficiently into the laser rod. Now this configuration is actually way more efficient than just placing a laser rod inside a spiral flash lamp tube. So the basic shape of a mirror for focusing the light from a finite distance is an ellipse. However, if the distance between the 2 points becomes larger or even infinite, as is the case in the telescope mirror, the elliptical shape transforms to a parabola. And if the distance is very small, let's say 0, the elliptical shape reduces to a sphere, where point 1 and point 2 are actually the very same point. Now from the previous you might get the impression that the difference in shape between parabolic and elliptical or spherical mirrors is quite large. But in fact, for most of the mirrors that are made by amateur telescope makers, where the diameter is, let's say, 4 or 5 times smaller than the focal distance, that's actually not the case. So the surface shape of a parabolic mirror is generally only a few microns different compared to that of a spherical mirror. And only when we go to much lower f numbers, the difference becomes more substantial and maybe even noticeable to the naked eye. However, even a few microns difference are very important, since visible light has a wavelength between 0.4 and 0.7 microns. And even surface deviations of a fraction of the wavelength can negatively influence the imaging quality. So let's focus a bit closer on the meaning of the term conic constant. So why use it? Well, it turns out that it's a very convenient way to define the surface shape of a certain class of aspherics with just one single number. So the name conic constant is derived from the word cone, and all the shapes we've discussed so far, the sphere or circle, the ellipse, the parabola, they're actually cross-sections of a cone under a specific angle. And using the geometry of a cone, you can very easily visualize the relation between a specific conic constant and the shape it's related to. So in this schematic I've drawn a cone with alpha defining the angle within the cone shape. And this cone can be dissected by a plane under an angle beta. Now the conic constant is defined by minus sine beta divided by sine alpha squared. So let's have a look what happens if we choose the angle beta, so the angle of the cut, as 0. Now if beta is 0, the conic constant is 0. And if you cut a cone under an angle 0, it gives you a circle as a cross-section. So for a circle, which is actually representing the cross-section of a sphere, the conic constant is 0. But if we dissect a cone under exactly the same angle as the angle within the cone itself, we see that the cross-section is a parabola. But if angles alpha and beta are equal, we know that the conic constant is minus 1. So for a parabola, the conic constant is minus 1. And any value of the angle beta between 0 and alpha refers to a specific ellipse, as you can see here in this visualization. So for ellipses, the conic constant is somewhere between 0 and minus 1. There are actually more different shapes possible. So in the case that beta is bigger than alpha, the resulting cross-section is a hyperbola. And the hyperbola has a conic constant below minus 1. Now there's one more additional shape, which is called the oblate ellipse, which has a conic constant larger than 0. It's actually the same ellipse that we saw previously, but then placed on its side. Now if you quickly look at the formula of the conic constant, in order to get to a positive value, we cannot use a real number inside the brackets, because squaring a real number will always result in a negative conic constant. So with an oblate ellipse, we need an imaginary number between the brackets, and for this reason the two foci are on an axis orthogonal to the optical axis. And this is actually a way to represent the imaginary part of a number. Now at this point, the wisest thing to do is state that this is far beyond the scope of this video. But in reality it's actually a bit beyond my intellect, so we will leave it here. But anyway, it's important to know that this shape exists, because we will actually encounter the oblate ellipse later in this video. Now all these visualizations are nice, but if you have a bit of a formula fetish like me, it's always nice to present a formula. So here it is, the formula that represents all the cross-sections of a cone. Now x and y are the coordinate parameters describing the surface shape in 2 dimensions, and the other 2 parameters in this formula are the surface radius r and the conic constant k. Now I don't want to go into much detail here, but just give you a little insight into the meaning of the formula. So if we fill in, for example, minus 1 for k, the function reduces to that of a parabola, which we've seen before in the visualizations. And if we fill in the value 0 for k, the relation between x and y actually becomes that of a circle. Anyway, bottom line is that if we want to build a reflective optical element or mirror that gives us a perfect image for not just one distance but for a range of distances, What we need is a mirror that has a variable conic constant. So as I said in the intro, one way to achieve this is by making a hollow mirror and then change the shape of the front surface by changing the pressure inside. Now, just to be clear, I didn't invent this. People have been making this type of mirror for many years, and I actually got inspired by a topic on a Dutch Astro forum, where a user named First Light was building variable mirrors with diameters of more than 600 millimeters. Now mine's a bit more modest, it's only 60 millimeters in diameter and about 5 millimeters thick. Unfortunately, I made this mirror quite some time ago and then quickly looked at it for an afternoon or so and then just forgot about it altogether. And I did not make any video material of the manufacturing process at the time. So that is why I will quickly show you how it was made in a schematic. I started out with two glass discs of glass ceramics of approximately 4 mm thickness, and one was ground concave and the other one convex with radii both approximately 300 millimeters. They were then ground nicely spherical against each other using silicon carbide grains in the range of 400 to 1200 mesh. Now next, the two parts were bonded together using blocking wax, and then the top surface was ground convex, also with a radius of curvature of 300 millimeters. Then after deblocking, I ended up with two main parts of this mirror, a concave front surface with approximately a constant thickness and a backlit that nicely fits the shape of the front part. The next step was making a cavity in the backplate to make the mirror hollow, and this was done by first applying a sandblast resistant layer at the edges of this part and then blasting a cavity of a few hundred microns deep in the backlit. Then I removed the edge protection and drilled a hole in the back of approximately 4 millimeters in diameter. The parts were then glued together at the edge using UV curable epoxy, and after this the front surface was polished using optical pitch polishing. So this is the result, and as you can see, the mirror is not coated yet with a highly reflective aluminum coating, and this is because in my setup the mirror shape can best be measured when the surface is still uncoated and reflects about 4% of the incident light. So to test it, I inserted a tube in the hole in the back and connected this to a syringe and a vacuum gauge. For testing the surface, I used an interferometer based on a design by Peter Seravollo, and here's a schematic. So coherent monochromatic light is generated using a diode laser, and the beam is then made strongly divergent using a gradient index lens with a very short focal distance. The light then passes through a beam splitter and a reference element, and this reference element contains one very accurate spherical surface. This surface reflects about 4% of the light back into the interferometer and is reflected by the beam splitter to the CCD. Now, the light passing the reference element continues to the uncoated concave mirror, which also reflects about 4% back to the CCD. So what we observe is optical interference between these two surfaces. And this allows us to measure deviations of the spherical shape in the mirror surface by evaluating the fringe patterns. By the way, any wavefront deformations caused by the rest of the optical elements, such as the beam splitter or the gradient index lens, are irrelevant for the interference pattern, because both beams use the same common optical path to reach the CCD sensor. So here's the setup in real life. The interferometer itself was constructed from, I think, less than 100 euros in surplus parts and materials. And here is the red diode laser and the gradient index lens, which can be adjusted a bit in position. Next is the beam splitter, and this is the zero-dur element which contains the reference sphere. Now, I made this element myself, and making the accurate reference sphere surface was actually the main effort in making this interferometer. And here's the CCD camera, which is basically just the PCB from a webcam. And it can be moved back and forth over a small rail to quickly adjust the image magnification. Using this tool, I could measure the surface shape of the mirror, and basically I recorded the interferograms at various pressures inside the mirror cavity. And these interferograms are actually just one-shot images, so no averaging or stacking. Now let me show you what an interferometric measurement actually looks like. So I start out here at the first pressure value and then record an image. Then I decrease the pressure in the mirror by expansion of the psi range, and you can see two things happen. First thing is a change in the focal distance of the mirror. If you look carefully, you will see the size of the interferogram change because of the change in focal distance. Also, you see the number of fringes increase because of the defocus. So, to correct for the defocusing effect, I move the position of the interferometer a bit. And by doing that, we can remove a large portion of this defocus and then measure the new surface shape more accurately. For evaluation of the fringe patterns, I used a shareware program by Dale Eason called DFT Fringe. Now, DFT Fringe has a few quirks, such as the fact that it refuses to present a round mirror as round, but I must admit that it's a truly amazing piece of software. Now, it uses Fourier transforms to convert the fringe patterns directly into a height map, and maybe the most amazing thing is that it's completely free, and that's quite remarkable given the fact that commercial interferometer software is quickly a few €1,000 or more. Now, among a ton of other things, DFT Fringe can also calculate the best conic fit for the surface, which we will use as a parameter here. So here's a 3D plot made using DFT Fringe, and it shows you the deviation in surface shape of the deformable mirror at atmospheric pressures inside compared to a purely spherical reference shape. Now, as you can see, at atmospheric pressure inside the mirror, the best fit conic is calculated to be plus 0.42. So in the initial state, the surface is actually an oblate ellipse. And this is the shape right after polishing with no additional corrections made on the surface. Now, the reason for this shape is that you actually need quite a lot of pressure during polishing. And because the front surface is quite thin and it's not supported by anything in the center, it's actually bending away from the polishing tool. So this leads to less material removal in the center of the mirror. So that's where this bump comes from. Now, it's possible to remove the bump by using a different polishing stroke, but instead I decided to leave it in there because I thought, let's just remove the bump by using a little vacuum. So next was to measure the surface shape at a range of pressures, and you can see that the best fit conic constants are ranging between plus 0.42 to minus 0.27. So by leaving the bump in the center after polishing, we actually cannot reach the shape of a parabola with a conic of -1, which is a pity. But the graph shows that it's possible to change the conic constant over a range of at least 0.7, which is good news. But I'm afraid there's also bad news. So when I was busy correcting the bump in the center and doing more measurements, I realized that the best fit conic value and accuracy of shape for this particular conic value are two completely separate things. In other words, if you look at the initial shape, the best fit conic is 0.42. But if we compare the shape with a theoretical shape based on the same conic, we see that there's actually quite a big error in the surface shape. And this error can be specified by the Strehl ratio. So a Strehl ratio is a measure to describe how good an optic is compared to the theoretical value. Basically, a Strehl of 1 means perfect and 0 means total trash. So the Strehl ratio for this particular example is only 0.4, which is not that great. So having arrived at my new insight, I went back to the previous interferograms and evaluated the quality of each surface looking at the Strehl ratio of the surface compared to the theoretical shape at the same conic. And here is what the curve of the Strehl ratio calculated in this way looks as a function of the pressure. So let me just bring the last two curves together in one plot and explain. We start out with an oblate ellipse at 0 millibar, which has a low Strehl ratio of 0.4. In other words, we start out with a badly shaped oblate ellipse. By lowering the pressure, we get to a spherical shape with a conic of approximately 0 and a Strehl of 0.72, which is actually, well, it's not that good, but it's a lot better. And the best accuracy of shape is found if we make an ellipse with a conic of minus 0.17. And in this case, the Strehl ratio is 0.8, which is, well, quite decent because it's almost diffraction limited. And from that point on the strail is going down again. So if you look at this graph, the strail ratio is only slightly acceptable in a very limited pressure range. And what we would like is the strail to be constant and of course as high as possible over the complete pressure range. So what is causing this? Well, basically it's a construction issue. So the shape is not only determined by the pressure, but also by the stiffness distribution of the various parts in the mirror. And a more constant strail ratio could maybe be achieved by making the front surface thinner or more flexible in a specific region, like on the outer parameter, or maybe it's best to add a thickness gradient to the front surface. And the bottom line is that it would take a considerable optimization effort to make a device that has a constant strail ratio over a large pressure range. So unfortunately, as a usable item, this mirror is a total failure. But as a learning experience, I consider it a success. Okay, that's it for this video. I hope you enjoyed it. I can totally understand if you have any questions, so feel free to ask them in the comment section.